All right, good afternoon. We're going to pick up right where we left off after a little bit of logistics. I have at this point added 50-some people to NB based on the sign-up forms. If you signed up after last night, I haven't added you yet. If you signed up before last night, I have added you, and if you can't log in, try both your full email address and just the part before the @ sign as your username. This is due to a weird glitch in NB that will be fixed sometime this semester. Try resetting your password, and if none of that works with both of those usernames, contact me and we'll figure out how to get you in. At the end of last lecture, we were covering binary space partitions, and after class, I got a couple of very good questions. And this is bad. Why is this bad? Yes? Exactly. Let me read you a little something. I looked up in Wikipedia something called the principle of mediocrity, which is not carefully studied at MIT. But it says, anything unique and peculiar to us is actually one out of many and is probably average. And this is used in various cosmological arguments about the existence of life in the universe and things like that. However, I want to apply it more locally to say that if you are confused, then probably a lot of your classmates are also confused. Most of you are typical of your classmates. And so if you're confused, you will be helping out a lot of your classmates by asking your question. So please do so during class. I have not yet tried making a rule against questions after class, but if I get too many of them, I might experiment with that and see what happens. One of the really good questions I got after class was for this binary space partition tree that we're creating, don't I need to worry about the degree of the nodes or the sort of bushiness of the tree? Do I need to worry about its depth and its, whether it branches out well and so forth? Wouldn't a deep tree be a bad tree? We know this, right? We're experienced with this from binary search trees and things, that if they're deep, it takes a long time to find things, right? So why did I not talk at all about the depth of the binary space partition? Yes, in the back.
So we worried about how many splits would happen, and the depth of the search tree, I guess, would be proportional to the number of splits we have.
Well,
Each split creates one more region.
I mean, we showed a pretty small bound on the number of splits, right? That there's only going to be n log n nodes. But with that many nodes, we know that the depth could range anywhere from log n to n log n. Why don't we care? Yes?
I guess my thought is that we're trying to save on computation time, and we're still doing that even if it's worst case, just straight. What's the mistake? We just be looking through a straight line, so having to compute all the.
Yeah, what do you mean by computation time? Or what is it that we're doing with this tree?
I guess we don't have to kind of recompute the depth of each polygon if we want to draw things like that.
Oh, but this is true of binary search trees as well, right? We don't recompute them, but it's still really bad if they're deep. Yes? Good. That's the key point. The only thing that we are using this tree for is to walk over the entire tree, right? We are not using, this is not a search tree, right? We in our minds as computer scientists, we see tree, we think search. But there are other uses for trees, and this is one of them. We're not searching for any particular node. We are traversing the entire tree in order to visit all of the nodes. And so that all that matters is the number of nodes in the tree, and how they are arranged is irrelevant. Okay? And just to sort of drill this home more clearly, I didn't talk perhaps enough about the uses of this binary space partition, right? A canonical use for the binary space partition is if you have a scene, right? Lots of polygons and things, a complicated building and objects in it and so on and so forth. And now you have a viewer who wants to move through that scene, right? They're walking through the building, right? And inspecting the objects, getting closer, getting farther, so on and so forth. Each time the viewer moves, you need to re-render the scene, right? If you don't have a binary space partition, you have to solve the rendering problem from scratch and do this kind of sorting and splitting that we talked about last time. If you have a binary space partition, all you have to do is walk over it. Okay? And so it is worth investing time in constructing the binary space partition ahead of time before somebody visits your building so that you can then do rendering very quickly as they wander through it because the shape of the building is not changing. Okay? All right, so that's the end of the story for binary space partition, unless somebody has any questions about it. If not, we're going to move on to the next topic, which I will freely admit is my favorite, which is minimum cuts. Okay. Quick question: how many people here have seen Max-Flow and the Max-Flow min-cut theorem? Just about everybody. Great. If you haven't, you should. Go find out about it. We will be referring to it several times in this class, and I'll assume you already have some basic knowledge of it. So we are familiar with ST Max-Flow, ST min-cut theorem. Right? The definition of an ST cut is a partition of a graph that separates two vertices S and T, and the value of the cut is equal to the number or total weight of crossing edges from one side of the cut to the other. Yes? And I should say, somebody already caught a sort of definitional error in the homework, which I will flag on NB. But in the homework, a cut is defined as a set of edges that separates the graph. However, that's sort of a backwards definition. First, you separate the graph. First, you divide up the vertices. And then the cut is the edges crossing between. So the cut is defined by the partition and not by the set of edges. Okay? So these are ST min cuts, which we've studied a lot in the context of ST Max-Flow because of the duality theorems. But today we're going to be concentrating on the global minimum cut, which is simply the problem of splitting the graph into two without any concern for particular vertices S and T. Okay? All that is required is that the two sides of the partition be non-empty. Obviously, you can have if you allow for a partition where all the vertices on one side, then the value of the cut is 0. But that's not interesting. So we want a non-trivial partition of the graph, and we're interested in how many edges cross the smallest of those cuts. This is equivalent to asking what is the fewest edges that you need to remove in order to, or the least weight of edges that you need to remove in order to break the graph into two pieces. Okay? And so it's asking sort of how fragile is the graph. And so it's actually a pretty useful quantity to be studying when you are worried about things like network reliability. The chances that your internet is going to go down because there's no longer a path between certain nodes in the network. Okay, and we'll talk about network reliability later in the semester. So does everybody understand the problem that we're aiming to solve? Can anybody propose an obvious algorithm given what we have on the board right now? Ford Fulkerson for what? Okay, so that's the question. How do we bridge from the Max-Flow to the minimum cut, right? Max-Flow, you need to specify an S and a T, and you can compute the Max-Flow using your favorite algorithm, right? Ford Fulkerson, Dennis blocking algorithm, push relabel, whatever. And when you finish, you have an ST Max-Flow, and that gives you an ST min-cut. But that does not solve the global min-cut problem, right? So how do we need to extend this? Yes? Great. Great. So algorithm 1 is compute the ST min cut for all pairs S and T. Right? So this will take you n squared max flows. So this problem is polynomial time solvable, right? Which is a nice thing to know to start with. Can we refine this a little bit? Yes. Good. So we can fix S and compute the ST min cut for all T. So this is only n max flows. Now at this point, I have to draw a distinction. With max flow, we sort of could start right from the beginning talking about directed graphs. Flow is a directed concept. And so you immediately start talking about directed graphs. And once you're talking about directed graphs, you can also talk about directed ST min cuts, right? It's the number of edges going from the S side to the T side. Okay? Now, we are going to be looking at the minimum cut problem in undirected graphs. Okay? You can define the minimum cut problem in directed graphs. But in that case, you would have to tweak this a little bit because you don't know if S is on the ingoing side or the outgoing side of the minimum ST cut, of the minimum cut of the directed graph. And so you would actually need to compute the ST min cut and also the TS min cut for all T in case S is on one or the other side. And so it would take you 2n max flows instead of n, but that's irrelevant asymptotically. And for a undirected graph, you don't need to do this because the cuts are symmetric. And so you could just assume S is on the inside and compute the outgoing cuts. And that gives you a solution. So n max flows. Question?
So I noticed that when you do this algorithm, if you have a node in one vertex and, oh, never mind.
Never mind. Okay.
I realized that.
Okay. I will never mind.
Maybe you can simplify the calculation for the max flow to some other node within the partition.
Yeah, so there's some interesting questions that you can explore about if you're going to be computing these n max flows, can you be clever about it somehow? Use the information from one max flow to sort of give you information about additional max flows. And in fact, it turns out that using these n max flows, you can construct something called the Gomery-Hu tree, which is a tree on the vertices of the graph. And you can find the minimum cut of any pair of vertices in the graph by looking for the smallest edge on the path between two vertices in the tree. So the Gomery-Hu tree, with only n numbers, encapsulates all of the n squared different ST min cuts in your undirected graph. It's a really nice, concise data structure and says that there's some deep structure about the ST min cuts in a graph. Okay? However, we are not going to be spending time on that today because, again, we are focusing on the global min cut of the graph. And so we're going to look in a completely different direction. So the first sort of people who looked directly at this global minimum cut problem was a pair of people named Nagamochi and Ibaraki. And they had this interesting insight that if you could solve a certain sub-problem, you could use it iteratively in order to find the global min cut. And the sub-problem that they identified was find any edge not crossing the global min cut. Suppose you had an algorithm that could find one edge that didn't cross the minimum cut, and they gave one. It actually runs in order m time undirected, for an unweighted graph, and in order m log n time for a weighted graph. So given that algorithm, how could you find the global min cut? Yes?
You'll contract the edge and repeat until you reach.
Great. So if you can do this, you can contract this non-min cut edge. Okay. In other words, you take your graph with all of its different vertices, and you find some edge that does not cross the minimum cut. You just draw a dashed line around the two vertices that you're contracting, and you say these are now going to be treated as a single vertex. I am going to take all of the edges going into either vertex, and I will combine them. Notice that this might create parallel edges, right? Even if you start with an unweighted graph, you might end up with now two edges going to the same vertex in your contracted graph. That's fine. Okay. But this is the basic operation of contraction, and all you need is this subroutine. Now you can contract, and now you've just reduced the number of vertices by 1. So you do this n minus 1 times, or n minus 2 times, and you're left with two vertices with lots of edges between them. What is the minimum cut of this graph? There's only one cut. That's the minimum cut. Problem solved. And now you can unroll the contractions, right? You know which vertices are inside each of these super vertices, and you have your minimum cut. Okay. So, really simple. This is quite a sophisticated subroutine. Like it's very tricky to prove that it works. It's a weird sort of greedy search, kind of like Prim's algorithm, but with a different objective. And it's very strange that it works, but it does. And with all the complexity inside there, you have a very simple algorithm, right? Find a non-min cut edge and contract it, do that n times, you have the minimum cut. All right. Well, it's a nice algorithm, but it does have all this complexity locked up inside of the finding an edge subroutine. So can we come up with a simpler procedure for finding an edge that's not a minimum cut edge? And I encourage you to remember what class you're taking. Yes? Yeah, why don't we take a random edge? So this is the contraction algorithm that we're going to be studying. We will simply repeat n minus 2 times. Choose a random edge. And contract it. And we'll just hope we get lucky. Okay. Now this class is going to teach us how to study our likelihood of getting lucky. Okay. But what's the intuition behind choosing a random edge? Why might we hope that that is a good strategy? Yes, blue shirt. Exactly. The intuition is that if you have something rare, a random choice is unlikely to hit it. Right? So the intuition is that a minimum cut is small. It involves only a few edges of the graph. And therefore, if you pick a random edge, it is probably not a min cut edge. Okay? Yes?
So, like, once you get to, like, almost the final step, like, wouldn't basically almost have the edge?
Very good point. So you are pointing out that as the graph gets smaller, the intuition begins to break down, right? But it is still a useful intuition. We just have to understand where it takes us. Okay? So there's another issue, which is that there actually are certain graphs where every edge is a minimum cut, is an edge of some minimum cut, because a graph can have more than one minimum cut. But for this analysis, for the intuition, right, we're only looking for a minimum cut, and so we can just concentrate on that one, right? And the point is that only a few edges are on that minimum cut. Every edge might be on some other minimum cut, but the one that we're trying to find only has a few edges of the graph. Does this make sense? Okay. So the intuition is that few edges cross what I'll call the target min cut, which is the one that we're analyzing this algorithm from the perspective of a particular minimum cut that we can't see, but the analysis can see, right? We can't see it as we're running the algorithm, but we can still study the algorithm from the perspective of that cut. Okay? Yes, a question. Exactly. Thank you for letting me clarify that. I'm going to present this in terms of an unweighted graph, but if you have a weighted graph, if the weights are integers, you can just pretend that the integers represent a count of edges and do the same thing. And if the edges are rationals, you can convert them all to integers by casting out the denominators and do the same thing. And if they're reals, you can treat them as limits of rationals. So the point is that if you just choose proportional to the weight, the analysis goes exactly as it would for just using an unweighted graph. Okay? All right. So how can we formalize this intuition? Okay, so that we can put some numbers behind our hope for good luck. Okay. We want to show that the minimum cut involves only a few edges of the graph. I'll actually turn that upside down and say, let's suppose that the min cut is C. Okay. Given that fixed value for a minimum cut, can we now prove that there are many edges in the graph, as that we can say that the number of edges in the whole graph is much larger than C? Yeah? Great. If the minimum cut is C, it means that every degree is at least C. Right? What does that tell us about the number of edges in the graph? Well, let's suppose we have an n-vertex graph. I should establish this for the whole semester. Every graph has n vertices and m edges. And I'm always going to forget to tell you that. And so when you see n's and m's, that's what I'm usually referring to. Okay, so if you have an n-vertex graph with minimum degree C, what can you say about the number of edges in the graph? Yes?
It's at least NC over 2.
Exactly. There are at least NC over 2 edges. Does anybody remember what this lemma is called? Yeah? Yeah, this is the handshaking lemma. Right? Basically, if you add up all of the degrees in the graph, you're counting each edge twice because each edge contributes to exactly 2 degrees. Right? So the sum of the degrees is twice the number of edges. Okay. But we've just argued here that the sum of the degrees is at least NC, right? And that gives us our result. Okay. Yes, question?
So eventually, as this algorithm gets smaller, like goes on a smaller graph, can we just use our other algorithm
Good question. Let's save that until I finish this analysis, okay? So we now have a bound on the number of edges. We can therefore say that the probability that I pick a min-cut edge, a target min-cut edge, is equal to C over M, which is at most C over NC over 2, which is 2 over N. We have now formalized our intuition that you are very unlikely to pick a min-cut edge. Is that clear? Okay, are we done? Can we now say that our algorithm finds a min-cut with probability 1 minus, that is, it only makes a mistake with probability 2 over n? Yes? Yeah, the problem is we have to keep going, right? So the probability that we succeed in this algorithm is equal to the probability that we never fail as we shrink from n vertices to 2. Right? So how do we analyze this probability that we never fail? Yeah, hand? Almost. So remember that what we set up here is the probability that we pick the minimum cut edge is 2 over n. So what's the fix? Good. So there's a 1 minus 2 over n, right? That's the probability that we don't pick a min-cut edge on the first try, right? Then there's a 1 minus 2 over n minus 1, which is the probability that we don't pick it on the next try, right? And so on and so forth. All the way down to the last pick, which happens when we have 3 vertices and we're contracting to 2. Okay? Now, why is it appropriate for me to write this all as a product? What probability law am I using here? Yes?
You're breaking it up. But you're still using some conditioning. You're conditioning on the fact that you haven't picked the min-cut.
Exactly. So this is the probability that I don't fail at n, right? This is the probability that I don't fail at n minus 1, conditioned on the fact that I didn't fail at n, and so forth. So this is a big product of conditional probabilities. Yes? And what does this conditioning tell me, right? If I didn't fail at n, what does that mean for the analysis that I do at this step? Yes? Yeah, it means the min-cut is still C because I didn't destroy it, right? My contractions can't make a smaller cut, right? They can destroy the min-cuts and make the global min-cut larger, but they can't make anything smaller. So if I didn't contract in the previous stage, my analysis for failure probability is still valid. And therefore, I can just multiply all these things together. Okay? So if I actually want to do this multiplication, I can simplify it by bringing up the denominators. Right? So over here, there's going to be like a 2/3, and a 3/4, and a and so forth. Okay? Sorry. Yeah, that's right. So what does this simplify out to? Oh, sorry, I did it backwards, right? Thank you. 1/3, 2/4, 3/5. No, wait a minute. The last denominator minus 2 minus 3, 1 minus 2 over. Yeah, the last one is 1 minus 2/3, which is 1/3. Okay, so what does this simplify down to? Yeah? What was that? Go ahead. Exactly. What's lovely about this is that everything cancels out, except we are left with a 2 at the and a 2 and a 1 at the end in the numerator, and an n and an n minus 1 in the denominator. Which, if you know your binomial coefficients, is n choose 2 inverse. Okay? So we now have the probability of success of this algorithm. It's 1 over n squared. Yay. No, wait. Ooh. This is not very good, right? But it's good enough. It's good enough to give us something. Okay? So this is actually very common in randomized algorithms, is that you have an algorithm that succeeds with some probability, but the probability is smaller than you would like. So if you have an algorithm whose success probability is too small, what do you do in order to get an algorithm that has a higher success probability? Yes?
You amplify it by just doing it over and over again?
Exactly. So a key idea has this really fancy name, amplification. And what it means is keep trying. Right? So in particular, if I try k times, then the probability that I always fail is the probability that I fail each time. Right? So how do I analyze that probability? Yes? And why can I raise the probability of failure to that power? Why is that an appropriate analysis? And why doesn't that conditioning make all of the math really messy? It's actually a slightly different logic, because when I had a success here, it told me the graph contracted and it changed the probability for the next success, right? In this analysis over here, does the first failure change the probability of the next failure or success? What am I relying on? Yeah?
Different trials are independent.
Exactly, right? I mean, I'm relying on this so much that I didn't even say it to you, right? But if you're going to run the algorithm a whole bunch of times, right, if you've designed it properly, you make the different runs independent of each other, which means that the probability that they all have a certain outcome is just the product of the independent, of the probabilities of the individual trials, right? So this is just going to be the probability of one failure raised to the kth power. Okay, so for our algorithm, that probability is going to be 1 minus 2 over n times n minus 1 raised to the kth power. And what's nice about this is that we can make it as small as we want by making k bigger and bigger. Right? Yes? Question?
Oh, sorry. I was going to suggest that about if K.
Yeah. So in particular, again, you pick the k to target a particular value, but if we set k equal to n times n minus 1 over 2, then this is equal to, 1 minus 1 over big number raised to the big number, which is 1 over e, or close to 1 over e. If we make it order n log n, then this number becomes equal to n to the minus, I need another letter, t. Sorry, let me be a little bit more careful about this since it's the first time we're doing it. If I make this number, say, t times n minus 1 over 2, then this times log n, then this becomes e to the minus t log n, which is, or about e to the minus t log n, which is, roughly speaking, n to the minus t. Okay? And this is a kind of target that we typically seek in randomized algorithms. If you're able to show that the probability of failure is inverse polynomial in the size of the problem, we say that this algorithm is succeeding with high probability. And implicit in this statement of with high probability is that it's in the parameter n, which is the size of the problem. Now, why do we like to use, why is this sort of shape of formula the one that gets this pleasant name, right? Why do we think about 1 over a polynomial as a good target for the failure probability of our algorithms? Yeah? Well, in this case, the success, this is the probability of success, or this is the probability of failure, right? And so the success probability is just 1 minus this. It's very close to 1 already, so you don't really need to talk about expected beyond that. Okay, yes?
Because we usually look at the behavior of the algorithm for large n.
Yes, and so that means it's nice to have a decreasing function, but why not 1 over log n, or 1 over log n, right? Like there are all sorts of decreasing functions, right? The reason is in the way we design algorithms, right? We'll often design algorithms where our algorithm will make subroutine calls to other algorithms, right? And if you think about an algorithm that is running for a polynomial amount of time, that gives the algorithm enough time to make a polynomial number of subroutine calls. And if those subroutine calls are randomized and all have a chance of failure, then, I haven't talked about the union bound yet, but we will soon, it's natural to just add up the failure probabilities of all the subroutines in order to bound the failure probability of your entire algorithm. So, if there's going to be a polynomial number of subroutines, you want each of them to have an inverse polynomial chance of failure so that the overall probability of failure of your algorithm is still small. Okay? So because we work with polynomial time algorithms, we are interested in polynomially small failure bounds, right? And you'll notice that here I can change the degree of the polynomial to be anything that I want by changing a constant in the number of trials, which doesn't do anything to the asymptotic runtime of this algorithm, right? So whatever polynomial I want, I can get it with asymptotically n squared log n trials, okay? So any 1 over polynomial failure probability with order n squared log n trials. Yes? Yes. So think about your an algorithm that you are designing, right? Maybe your algorithm is an algorithm that uses minimum cut as a subroutine. Okay? So your algorithm is going to fail if ever this min-cut algorithm fails, right? So we want to bound the probability of any failure in all of your calls to the min-cut algorithm, right? Now, of course, the more times you call the min-cut algorithm, the more likely it is that you'll have a failure, right? But how many times can you call the min-cut algorithm? If you're designing a polynomial time algorithm, then you only have time to make a polynomial number of calls to the min-cut algorithm, right? And if you only make a polynomial number of calls and the probability of failure on any one of them is 1 over an even smaller polynomial, then by the union bound, which I will introduce shortly, you will not have any failures. Make sense? Any other questions? Okay, so just to wrap this up, we have now given a, we now have an algorithm that has a high probability of success instead of a low probability of success. What's the overall runtime? Well, we're running the contraction algorithm n squared times. We need to figure out how long it takes to run it once, right? The naive method would just work with the graph sort of in whatever data structure you want, and you would have to sort of somehow look over all of the edges and pick one at random, and then you'd have to do this contraction process. And if you think about it, you know, looking over the edges and picking one at random probably takes you linear time, and then a contraction also takes you time to just sort of update the shape of the graph. So it's probably like m time to pick one edge, and then you have to do this n times, so it's going to be mn time. Turns out that if you're cleverer about it, if you use an adjacency matrix representation, you can kind of compute the number of, you can keep track of the number of edges or the total weight of edges as you merge the adjacency, as you merge the rows and columns of the adjacency matrix and reduce the runtime of the contraction algorithm to n squared. Or, as you will show in your homework, you can actually see this as sort of a variant of the minimum spanning tree problem if you look at it the right way, and then you can run the contraction algorithm in order m time, okay? So the base contraction algorithm can be implemented in order m time. You need to do n squared log n runs. And so overall, you have a runtime of mn squared log n to find your target min-cut with high probability. We say this so often that we just abbreviate it to WHP. Okay. And now we're done with min-cut. Okay. Now we're actually not done with min-cut. I'm going to have another whole lecture or two about it later on, because there's a lot of ways we can improve this. Okay. This runtime is actually not really that competitive. I mean, it's roughly the same as you would get using your many max flows approach. Right? We didn't carefully run through the runtime, but if we're going to compute n max flows, each of them takes about order mn times. So the max flow approach also takes order mn squared in general. Okay. But we can make a lot of improvements on this. One is actually just an observation. We proved that, that this algorithm finds our target minimum cut with probability roughly 1 over n squared. Now, I didn't say which min cut was our target. So let me ask a kind of related question. How many min cuts can a graph have? Yes?
If you allow the weights to get
Well, in the best case, right? If it is true that you can pick your arbitrary real numbers so that there's only one minimum cut, but like a graph has 2 to the n cuts, right? There are 2 to the n ways to partition the vertices. Might they all be min cuts? Yes. Elaborate that a little bit. Exactly, right? The point is that each min cut is found with probability 1 over n choose 2. Yes? Because we didn't say which one we were paying attention to when we did our analysis. Right? Which means that the expected number of min cuts found is equal to the actual number divided by n choose 2. Yes? But we also know that we can only find one cut, because the algorithm, when it finishes, just finds one cut. So this immediately tells us that the actual number is at most n choose 2. So this is a very weird way of proving an upper bound on the number of minimum cuts in the graph, right? We never looked at them. We said nothing whatsoever about the structure of the graph. We just have this argument based on probability that each of them is likely to be found, so there can't be too many of them. Yes?
This requires that each vertex has an edge.
If the graph has empty cuts, then you can have an exponential number of them. Yes. If the minimum cut is 0, if the graph is disconnected, then you can have an exponential number of cuts. So I am assuming here a connected graph. Okay. Other questions or thoughts? Yes. Oh, it's just the contraction algorithm. That's what I called it. Yeah, I mean, it does get called Karger's algorithm. It was something I did in graduate school, which is why this is my favorite problem. So there's lots more to say about this, which I'll mostly save for another lecture. Here, now that we know that there are n choose 2 min cuts, you can actually argue that this algorithm, when you run it n squared log n times, will find all of them with high probability, right? Because we just gave a proof that with high probability you find a particular target cut, right? You can just argue that the probability that you find any of them is still small. That you miss any of them is small. Okay, and we'll come back to that later. But there's another question I want to ask about this algorithm, which is we've driven the probability of success really close to 1. But can we make it 1? I mean, can we be sure that we have found the minimum cut? Right? I run the algorithm a gazillion times and it never shows a cut smaller than 5. Does that mean the min cut is 5? Yeah?
One thing I'm thinking, but I feel like this is, we wind up kind of being themselves, maybe this is this. But I guess we could, like, do maximalism and check, but I feel like that's not enough.
Yeah, I mean, you could. So what you're saying is that there needs to be some kind of check. Like just this claim that this algorithm only found cuts of size 5 and bigger, that does not prove that the minimum cut is 5, right? So this algorithm has no certificate of success or certificate of correctness. Okay, and so this is something that happens, it's not uncommon in randomized algorithms. You have an algorithm with a high probability of success, but no way to be sure. that it actually, right? It's not just that there's no way to be sure it will succeed, but that you can't be sure that it has succeeded after you've run it. There's no certification. And so these are known as Monte Carlo algorithms. And they are one of the main classes of randomized algorithms. Now, as a contrast, another kind of randomized algorithm that we will see frequently is an algorithm that is certainly correct and probably fast. Okay? And this is what's known as a Las Vegas algorithm. And I forget who came up with these names. You know, back in the early days, you get to have fun naming basic things. So you want to keep in mind this distinction between Monte Carlo and Las Vegas. Okay? We have seen an example of each class. Okay? I've just shown you a Monte Carlo algorithm. What is an example of a Las Vegas algorithm that we have seen? Yes. Quicksort. So we have a guarantee that when Quicksort finishes running, the list will be sorted. It is always correct. However, it might be slow. Okay. The MinCut algorithm is always fast. There's no randomness in its runtime. Well, there's a little bit, but it doesn't. It has a nice it's upper bounded by this quantity. It's always fast, but it might be wrong. Okay, right? So this is move fast and break things. This is careful specification and design of your software so that it doesn't break. What's the relationship between these two? Right? Suppose that you have a Monte Carlo algorithm, but you want to be confident in its answer. Right? How can you achieve that confidence? Well, you already pointed in the right direction. If you want to convert a Monte Carlo algorithm into a Las Vegas algorithm, it requires some kind of answer checker. Or a certificate of the correctness of the answer. Okay? And so, in the case of Global MinCut, we have a certificate checker. We can just run lots of max flows and check that the value reported is the correct value. It's kind of a stupid certificate because it's also a way of constructing the answer. But often it's easier to check an answer than it is to find one, right? This is why we have the class NP, right? So there are many cases where you can get a certificate of correctness of the answer. If you if you check the certificate and it turns out that the answer was wrong, what should you do? Yeah? Run the algorithm again, right? We've already talked about this repetition idea, right? So what you can do is just repeat running the algorithm until the certificate checks out. And we will fill in the details of this shortly. But basically, if the algorithm has a decent chance of success, then the expected number of runs until you succeed is small. And that means that the expected runtime of the algorithm that runs until it checks the certificate will be roughly the same as the runtime of the Monte Carlo algorithm. And so you'll get an algorithm which is always correct, but still has a fast runtime in expectation. Okay. What's the alternative? Suppose you have an algorithm that is, usually fast and always right, but you're in a hurry. So you want to be sure that you get your answer quickly and you're willing to sometimes make mistakes. What should you do? Yes, Bowtie. Exactly. What you can do is stop early. Okay? And this will require some analysis, which again we'll get to in a little while. But basically, if the algorithm has a fast expected runtime, then if it runs for a lot longer than its expected runtime, you can just stop it and make up an answer, right? And we have various bounds like Markov's inequality, which tell us that it's not likely to run much longer than its expectation, and therefore you are unlikely to have to stop it, and therefore you will usually get the right answer. Okay? So I will formalize both of these shortly, but that is the general idea. Are there any questions about our exploration of this weird Monte Carlo algorithm and the relationship between these two different styles of randomized algorithms? Okay, let's take a 2-minute break for everybody to run up and down the stairs, and then we will resume.
So I registered on MB like today after like I got added, and then like my currently like my MB account is not linked to my email for some reason.
Yeah, that's fine. Like I said, if you registered, if you got onto the sign up form today, then I haven't yet added you to NB, but I will do so after class.
I think that I got an email saying that I was added to NB, but at the time I didn't have an NB account.
No, if you're added to NB, then you have an account. The one was created when you were added.
Like, what's the username and password?
So the password is, you'll have to reset the password in order to log in, but you'll have an account.
Like, email is my MIT email, correct?
Yeah, and that's your username.
Like, I got confused and I created another account that also had the same email. Would that cause issues?
That's an interesting question. I don't know if I'm not sure you should be able to do that.
Like, it didn't stop me from doing that.
All right, interesting. I'll have to look into it after class.
Okay.
You may have hit a bug in the system, but we'll figure it out. Send me an email.
So I noticed that if there's a vertex, like if the graph is not connected, then the algorithm fails because.
Well, if the graph is not connected, you'll eventually end up with
Like,
disconnected vertices, and you'll know.
I guess we'll know.
Yeah, so, I mean, it's also easy to check that in linear time before you start.
Couldn't we have just said that we just take all edges and take a uniform way to like a
Uniform
sequence?
distribution.
Yeah,
Yes,
yeah,
random permutation.
Yeah,
Yes.
and then just like say that the probability we succeed is just like the probability the start is all other edges and then the last edge is the C. So we get like the entire thing to be like n minus C factorial over n factorial just immediately.
Well, n minus c factorial over n factorial is going to be a much worse bound.
Isn't it the same?
No, n minus c factorial over n factorial is going to be about 1 over n to the c power, right? And so if the min cut is large, it's going to be a tiny number.
Wait, no, sorry. It's
Right? Your idea of taking a random permutation is actually how you can get a more efficient implementation of the algorithm. But the analysis basically replicates this. It doesn't change the analysis.
oh wait, actually maybe it's not equivalent to take a random permutation because instead.
No, it is in fact, so as you will see in the homework, if you take a random permutation, essentially if you take a random permutation of the edges and contract them in that order, you are implementing this algorithm.
Yes, but we don't arrive at the same kind of bound, right?
Yeah, you get exactly the same bound. The thing that may be throwing you off is that if you have a random permutation, then a lot of the edges that you contract are already going to be loops, right? They are already going to have both endpoints on the same vertex, and so it won't change anything. Sure.
So I suggested at some point, like
stopping this algorithm at like.
Yes, and that is something we will talk, that works well, and we will talk about it in a future lecture.
Okay.
You have to do it properly. It takes us in interesting directions. All right, let's resume. So for the remainder of this class, I unfortunately have to do some complexity theory. As I mentioned last time, I'm not a big fan of complexity theory because it's all about what you can't do, and I hate the pessimistic, depressing attitude. But another thing that complexity theory has done is given names to interesting categories of algorithms, and I want to be able to refer to those names as we are talking about randomized algorithms. So here we'll have a very short introduction to the complexity theory of randomized algorithms. So since we're talking about complexity theory, we need to have a very sort of pure and abstract notion of randomized algorithms, right? We need to say, what is a randomized algorithm? And really, to answer that, we first have to say, what is an algorithm? Right, and then we'll just sprinkle in some randomization. So, you know, in our field, we define our algorithms as things that can run on Turing machines. But those are really painful to think about. So we often move to models that have RAMs, right, large amounts of state. That we can read and write arbitrarily. You have to be a little bit careful to be sort of formally equivalent to a Turing machine. You need to use something called a log cost RAM that doesn't allow you to store really huge numbers in your RAM. You basically need to have a finite word size. Otherwise, you can do sneaky things like encode an entire algorithm in a giant real number and store it in your machine and get answers to things in constant time. But if you charge for storing big numbers, you get something which is basically equivalent to a Turing machine. Also in complexity theory, we generally talk, instead of talking about the sort of optimization problems like sorting and min-cut, we instead simplify to what are called decision problems, right? Which divide a set of inputs into some inputs that you accept and some inputs that you reject. In other words, we sort of shrink down every algorithm to being one that just outputs a single bit or a single yes or no answer. This isn't really a major constraint because, for example, we can talk about the problem of deciding is the size of the min-cut smaller than k, right? That's a decision problem where you feed in a graph and you get back a yes or a no answer. And if you can answer the decision problem, then you can use binary search in order to actually find the minimum cut. So this isn't really a major restriction, but it does sort of simplify our discussion of complexity theory because we no longer need to talk about outputs aside from accept or reject. So a language is a set of inputs that is like a subset of the inputs, and the language that is accepted by a particular algorithm or a particular Turing machine is the set of inputs that it accepts. Right? So a language is a subset of possible inputs, and we say that a particular machine or algorithm accepts a certain language or a certain set of inputs. A complexity class, or sorry, let me write that. A language is a set of inputs which is accepted by your given algorithm. And now we can talk about a complexity class is just a set of languages. And in particular, we're going to talk about the set of languages that can be accepted by a certain kind of algorithm, okay? Or a certain kind of machine. The one we're probably all familiar with is the set of languages. that can be accepted by a machine or algorithm running in time, polynomial in the size of the input. So the decision problems for minimum spanning tree and max flow and basically everything that we have a polynomial algorithm for is in P because there's an equivalent decision problem that can be solved in polynomial time. Now, probably the second most famous complexity class is NP, which is like P, but non-deterministic. And there are a number of ways to define what a non-deterministic algorithm is. One, to say that it's a Turing machine that makes non-deterministic choices in each of its steps. But an equivalent definition that is better suited to our randomized algorithms class is that you have a problem that can be solved in polynomial time given a polynomial amount of non-deterministic advice. Okay, which you should just think about as a polynomial in the input size string of zeros and ones. Okay, and mapping this back to our standard notion of NP, right? The idea of NP is that it's algorithms where you can check the answer if somebody tells you the answer, right? That's a sort of an intuitive definition of non-deterministic polynomial time, right? If you have a traveling salesman problem, it's hard to solve, but if somebody gives you the solution to the traveling salesman problem, you can check that it's short, right? If you have a satisfiability problem, it may be hard to find the satisfying assignment, but if somebody gives you a satisfying assignment, it's easy for you to check that the assignment is in fact satisfied. And so that thing that they're giving you is this arbitrary string of advice, a hint about what the answer is. And all your algorithm has to do in polynomial time is verify that, verify the answer. Okay? You know, from a complexity theory perspective, you can have other kinds of advice. It doesn't have to give you the answer encoded as an answer, right? As long as there is some input advice that causes the algorithm to produce the correct output for every input, that is in NP. Okay. So this is our background, but now we can start introducing the you know, once we have these complexity classes, we can also talk about interesting ideas like polynomial time reductions. Right? The idea of a polynomial time reduction is that if you have a problem that is in a particular class, and you're able to take a different problem and transform it in polynomial time into the problem you already put into the class, well, the new problem is also in the class. You can also use these notions of polynomial time reductions to talk about completeness. The complete problems for a class are basically the hardest problems in the class. They are the problems that you can take any other problem in the class. Like, if you can solve the complete problems in the class, then there's some mechanical process to take any other problem in the class and transform it into this complete problem. So if you can solve a complete problem in some way, you can solve any problem in the class in some way. And this is where we get the notion of NP completeness, that, you know, there are certain problems like SAT and TSP where if you can solve those, you can solve any problem in NP. Okay, but this applies to any complexity class, right? There are also P-complete problems and so forth. But now we can get into the randomized complexity classes. And randomization occupies a very interesting middle ground between P and NP. The idea of a randomized algorithm they also have an advice string. But unlike the advice string in NP, which is carefully selected to be the best possible advice, the advice in a randomized algorithm is just a random string. Okay? And that for the complexity theorist, is the definition of a randomized algorithm, is that it is an algorithm that receives an input and also receives a random advice string, okay, of a certain size. And you talk about the expected or likely behavior of the algorithm given this probability distribution over advice. And I should also say that it's actually uniformly random. So it's just a uniformly random sequence of bits is the advice. Okay? So everybody understands the sort of basic idea of how you fit randomization into the complexity classes? Because now we're going to start naming different kinds of complexity classes. Okay? So the way, I mean, if this is the complexity theory perspective, if you come back to an algorithm, right, you don't, in general, imagine that your algorithm is actually given a random string like this. But a randomized algorithm is making random choices, right? And the way you connect these is you say that when my algorithm is making a random choice, what it's actually doing is going to the random advice string and grabbing the next bit off of the random advice string. Right? Now, if I literally am only grabbing the next bit off of the random advice string, that only gives me a coin flip, right? How do I get from a coin flip to choosing a random edge, right? Or choosing a random pivot? Well, this is about how you take a sequence of bits, of random bits, and turn them into sampling from a given probability distribution, right? And that's on your homework. You will see in your homework that you can take this source of uniform random bits and turn it into whatever kind of randomness you need for your algorithm. Okay? So it's sort of universal. So now that we have that, we can start defining complexity classes. So the first one, ZPP, is zero error probabilistic polynomial time. And so under the sort of model that we just gave, what this means is that this algorithm always gives the correct accept reject decision. And the expected runtime is polynomial in the input size. Okay? So there's an algorithm that uses the randomness. It always gives the right answer. The randomness helps it go fast. What is our colloquial name for these kinds of algorithms? Right, I gave you these two categories. Which one is this? These are the Las Vegas algorithms. Okay. The next class is called RP, which stands for randomized polynomial time. And remember, we're talking about decision problems here. This is an algorithm that is always polynomial time. And if x is in the language, if x is supposed to be accepted, then, if x is not supposed to be accepted, if it's supposed to be rejected, that means that the algorithm rejects. On the other hand, if x is in the language, it means that the algorithm accepts with probability at least 1/2. I will write this as a of x equals 0, and I will write this as a of x equals 1, just to save myself some writing. Okay? So this characterization is known as one-sided error. This algorithm never has false accepts. It never accepts something that should be rejected. However, if something should be accepted, it might accidentally reject it. Okay. Now, this corresponds to which of our colloquial labels? Yeah? Right. These are the Monte Carlo algorithms. Now, I will point out here that the exact number, 1/2, doesn't matter. Okay, so suppose that I change the definition here to be 1/4, or 1/17, or 1 in a million. I claim it is defining exactly the same complexity class. How come? Yes? Exactly. If the running time is some constant, then repeating the algorithm a bunch of times, what will that do? Well, it will never cause you to accidentally reject because the error is one-sided. So what you can say is, I'll run the algorithm a bunch of times, and if it ever accepts, I will accept. Yes? And that means that I can increase the probability of success, or drive down the probability of failure, sort of geometrically fast, using the same sort of product of probabilities argument that I made for the min-cut problem. Yes? In fact, you could even have a 1 over polynomial in n probability of success, and you can still use the amplification technique. That's exactly what we did with the min-cut algorithm. Okay? If the probability of success is 1 over exponential, this doesn't work, right? But if this is big enough for amplification to do the job. Okay? A question? No. I will also mention here co-RP, which just reverses the notions of accept and reject. And it has its one-side error in the opposite direction. So co-RP means that it always accepts things that are supposed to be accepted, and it has a 50-50 chance of rejecting things that are supposed to be rejected. Okay? Now, I put in this constraint here that it is always polynomial. So you might be a little concerned that I've left out some coverage. What if I have an algorithm that's expected polynomial time, right, and has these characteristics? That's not technically in RP, right? But what can I do if I want to take this algorithm that has expected polynomial runtime and make sure that it always has polynomial runtime? Yes?
Like you could say like try to run the algorithm for time like say like n times expected runtime, and like and then like if like your algorithm does not terminate like in like this right amount of time, then you could just like
make up an answer. Yes, that's correct. And so again, we already talked about this, right? This idea of just truncating. If an algorithm is a Las Vegas algorithm and you want to make it Monte Carlo, you just stop early. And there's only a small chance of it taking too long, so you're unlikely to stop early. And the one-sided error nature of RP tells you what output you should choose if you stop early. Right? If you stop, right, you never want the algorithm to accept something that should be rejected, but it's okay for it to reject things that should be accepted. So if you terminate the algorithm early, you should reject, because that way you're never going to make an accidental accept, right? For co-RP, you do it the other way around, right? So these really capture the two classes that we colloquially identified. Something interesting, which I will prove for you next time, or maybe you'll prove it for yourselves, I have to decide, is that these classes are related. ZPP is equal to RP intersect co-RP. So if you have a problem that can be solved by a Las Vegas algorithm, you can solve it with, you can find a Monte Carlo algorithm for the same problem. And you can make it either have one side, you can make its one-sided error be in either direction. On the other hand, if you have a one-sided error, if you have two algorithms that have opposite one-sided errors, then you can get yourself a Las Vegas algorithm from that. Now, with the min-cut algorithm, we only had one-sided error in one direction. And that is why it is not obvious how to transform the min-cut algorithm into a Las Vegas algorithm. Okay. All right, I'm afraid I'm out of time. I'll sadly have to do a little more complexity theory next time. But we will then move forward in our exploration of randomized algorithms. And I think you now have enough to do the whole problem set. I think I left the complexity theory for next week. We are now going to hold office hours for the problem set. And I think we're going to do it in the lobby of 5th floor, or did you find a different room for it? Okay. For the first problem set, office hours will be in the G5 lobby.